So in this module, we'll continue to discuss the concept of vector field and flow visualization from a perspective of visualizing scientific data. In particular, for flow visualization, we'll focus on four main concepts of computing and visualizing streamlines, path lines, streak lines, and timelines. So those are some of the key aspects, but they are not the only one that are being used in flow visualization. In general, there is actually a fairly broad family of techniques that one can bring to the table when visualizing vector fields and flow in 2D and 3 dimensions. I just mentioned the aspect of we want to give a primary focus on streamline, path lines, streak lines, and timeline. But there is another variety of techniques from Lagrangian coherent structures, texture-based techniques, line, integral, or convolution are very popular, in addition to various constructional grids and additional derived techniques that we'll be looking at much later in the class. In terms of domain, where the flow is defined and visualized, we can see that we can have two-dimensional flows either on the two-dimensional plane or surfaces embedded in 3D. When you visualize two-dimensional flow, there is the advantage that you could show the flow in a very high degree of detail in a single view. You can have a very high density in terms of the representation of the flow lines, structure where things merge and separate and so on. When it goes to the 3D case, here on the bottom right, you will quickly see how the visualization gets complex and cluttered because of occlusion and depth perception. And so often one can use a mix of, say, two-dimensional representation as a cross-section, plus actual lines that follow the flow in different structures, but especially in that case then rotating through the data and so on, or visualizing different lines with different starting points, as you will see later, becomes particularly important. So let's see more precisely what those four concepts mean. So let's start from the streamlines. Streamlines are curves that are parallel to the vector field at every point. So kind of a little bit more formally, one can think of those as being represented as an integral that from a starting point evolving through a flow. Notice that here we're not including in this description a time parameter because those really make sense in a steady vector field. And so in particular, you take a particular location and then you follow or integrate along the direction of the flow. And so you have a curve that in every location is tangent to the vector at that point, representing the vector field. And so here we can think of static velocity in the sense that we're thinking of a fixed vector field over time, so not with including time variation. So path lines are in some sense more realistic because basically you cannot really have a streamline unless you really have a steady vector field, which would be very rare in the real life. For a path line, it's really the trajectory of a particle, technically think of that a massless particle over time evolving in a vector field. So here would be the the new integral representing the trajectory from the initial starting point. And notice that now the term representing the vector field is dependent on the parameter u that ranges from the beginning to the final time. So this is in a way more realistic in terms of thinking about releasing a particle in a flow and then let the particle evolve and keeping memory, keeping track of the trajectory that that particular particle, which we think of calling a seed, would take over time. So going to the next level, we look at the idea of streak lines. So this is a little more complex, but again more realistic. So it comes from the idea of the experimental case where people release a dye into a fluid, for example, and then you see as you continue to release the dye, the trajectory that's being described. So the integral now looks very similar to the case of pipelines, but the difference is that instead of just following a particular particle, there is a new seed created at the original location. So that's why the name streak line. So the streak described by the continuous release of the particle from a particular point. Obviously, if the field was perfectly steady, there would be no difference between a streak line and a streamline, but in practice, they are different. A final concept is the one of timeline, and we'll see a few examples of those. This one conceptually is kind of similar to the case of the streak line in the sense of the trajectory described by a set of particles. So obviously the integral is the same. But the difference is that instead of releasing a number of particles over time at the same location, we have a set of particles released instantly, basically like a front, in different locations in the flow. So we'll see that front evolving, and then timeline are much more powerful in terms of understand the difference in speed of the flow in different locations. So in some sense, the first three tend to be emphasizing more the direction of the flow, while the last one tends to emphasize more the difference or relative speed in different locations of the flow. So if we think of a flow in 2 dimensions and then extrude the time as a 3rd dimension in the flow, we will see how, for example, streamlines being related only to steady vector fields, at every instant we will have a whole different set of streamlines, right? So here in the later time steps versus the initial one, there is a full set of streamlines that are different from each other. They are, in some sense, unrelated, unless the vector field is the same. When we talk about path lines, then we have all the evolution over time, and then we have the structural curves we'll later show in animation, so there you see how those kind of evolve over time. And similar for a streak line, but here you see the location where the particle continue to be released over time, and then how they create a streak over time. The timeline, again, is more interesting because here if we have a set of points where we release a set of particles, because of the structure and the direction of flow, this front could start deforming, propagating through the flow, and give a sense of how things evolve and how quickly they do. So on the left, we see a set of particles embedded in a vector field, a 2-dimensional vector field. And so we see that being the field unsteady, it's kind of hard to understand really what's going on. If we visualize this, because then the problem is really that we have to memorize where the things evolve. When we visualize in the space that we used before, at least you can start seeing how the field changes over time and then how the particles evolve in a different way. And so this is kind of a conceptual model where, in a way, a two-dimensional plus time vector field is represented as a single three-dimensional entity, which is easier to interpret. For example, if we look at streamlines in a 2D scalar field over time, you can see how at every instant we have, in a way, a full description of a field, and that field keeps changing over time. So we have an instantaneous line that evolves in a certain direction, and then this set of line changes over and over. So while streamlines are very powerful to analyze a snapshot of a particular vector field, they actually kind of lose track of coherence over time. And that's where, for example, path lines can be more powerful. You have a set of initial points that you start with, and then you see how they evolve over time. And so that gives a more realistic sense of what happens to the points in a particular location as they evolve over time within this time-dependent flow. And again, so for steady, the strings are perfectly fine, and many times you have to visualize and analyze individual time steps of a field, so like here or like here. But again, if I have to have a sense of where a particular particle goes from beginning to the end, it's very hard from a set of streamlines. While a set of path lines tell me very clearly, oh, you start from a certain location. Say from here, you end up in this particular different location. And so this is kind of looking the overall. So this gives a better sense where, in the case of an unsteady flow, but if you think of that as a sequence of steady flows, every cross-section is basically a separate field. It's very hard to see. We get a sense of there is some kind of rotation, but we don't know, say, a particle starting from a certain location where it's going to end. In the case of path lines, so in fact here we're kind of mixing the two types of visualization. On the cross sections we have a kind of a steady visualization, but now we take a particular line with a particular flow, and we can follow that over time, and so we get an intuition of the structure of the flow as it evolves in the medium. So timelines are a nice complement together with strict lines when we look at a particular flow. So here I'm taking a short video clips, a clip of the long video that I gave a link in the first class regarding vector fields and just in the previous class. So here we see the strict line. So in this fluid evolving over time, there is a release of continuous release of particles in this particular location, and those evolve. This is a steady field, so there would be no difference with streamlines. What's interesting is the insight we can get from timelines, because if we release those particles in a particular front, we will see how that front evolve over time. So for example here, so if I mark, say roughly the original front is in this location, then we can see how that front evolves, and here we have a set of releases. And so in the later stage, now this is the new front. So if we follow a straight line on the top side, it travels really farther ahead. A straight line that travels on the bottom start falling behind. And so in terms of horizontal component of the speed, the top flow is faster than the bottom. And you can see that in the left view, this would not be visible. So a perfectly reasonable hypothesis of timelines would be kind of vertical lines of this type, and that would be wrong information. The reality is that given the structure we see on the right, so in each of those straight lines, the advancement gets kind of skewed with faster advancement on the top, and so the particle that was released, say, at the same time here reach this particular location, at the top will be a little bit farther ahead. And so that gives a better understanding of an unsteady flow as it evolves over time. And so, yeah, here you see again this evolution, and then you have a set of those timeline moving forward over time. So we look at those general concepts of stream lines and path lines that go through the evolution of the vector field over time. And in each location, there is exactly one streamline and one path line. And so this is an important statement of how they are distinct from each other. While things are more complicated in terms of straight line and timelines, because as they evolve, things can cross and so on, it makes it harder to describe. So an important basic statement is that in the case of a steady vector field, streamlines, path lines, and straight lines are effectively the same. They coincide. Timelines are kind of an orthogonal concept, but those three distinct concepts collapse together. To conclude this module, so we look at carefully at the definition of streamlines, path lines, straight line, and timeline as some fundamental building blocks to build effective flow visualization techniques for application in science and engineering. In the next module, we'll start focusing in terms of integration techniques and how to compute practically these different type of lines in terms of an algorithm that can be coded on a computer.